Hello everyone, we are on Unit 4, Lesson 3 today, and it's interpreting and using function notation. So we'll just go ahead and just leap right into this. Essentially, the thing that I want to make sure that you realize, by now hopefully you realize this, that when we talk about this, now, so far you've been talking about graphing stuff as x comma y, which is fine if you have x's and y's. Now we're just, with the use of functions, now we're just changing the input, okay? So now our input is something like t or time or something like that. But here's the big change, okay? So now the output is some function at that independent variable, that input of t, okay? So this is what we're graphing here. So we have like t down here, and we have f of t on this axis. And you have some function here. I'll just call it f because that's the function that we're talking about. So that's what's going on here. There's nothing outrageous about what we're doing. It's all the same thing that you learned before in single and double variables. The big difference here is now we just change the letters. Okay, so now it's t and the function at t. So it's just notation is all we really have done on this thing. It's just change notation. All right. So to begin with, is have the first one, 3.1, observing a drone. So the drone starts off here at time 0. It's at height of 0. And over the span of about 2 seconds, it goes up here to its max height. And that meter could be anything that you want. It could be 1, 2, 3, 4. It could be 5, 10, 15, 20. It's whatever. There's no scale on this, so we don't really know. And you don't need to know at this point for these questions. Goes up. Has the same height all the way out here till 5 seconds, and it comes back down till it lands on the ground at 7 seconds, and then that's its height is 0. So we got to decide which function value is greater. So we're going to get like 4 positions here, and we're going to find out which ones are true. Okay. So let's see, between f of 0 and f at 4. So f at 0 is just a height of 0, and f at 4 is 4 units up here. I'll just go ahead and label these as 1, 2, 3, 4, just to make it simple. So obviously that's on the ground, that's up in the air, so that one is bigger. And then they want you to compare F2 and N5. F2 is at 4, F5 is up here, it's 4. So these are actually the same. There's another degree. These two are equal to each other. They're going to control a function at time 3 and function at time 7. So function at time 3, it's like the maximum, and at 7 it's down here at 0, so f3 is bigger. And then they got f at t or f at t plus 1. Well, that one really depends on where you're going. All right. If I say t is 0, then t plus 1 is right here at 1 second, and that would be larger. And if you start at t equal 1, then t plus 1 is the number 2, and then yeah, that t plus 1 is larger. But then you get through like in here, and they're not going to be the same. All right, they're not going to be one greater than the other. They're going to be exactly the same all the way through here, between 2 and 5. As long as we stay in there, they're all the same. And then when you go down there, it's obviously going to be the opposite way around, where f at t plus 1 is going to be small and f at t will be larger. So it really changes. So I just circled this one and I said only at t equals 0 and 1 will that be true. So that one's a little bit sketchy, but it makes you think. Okay. And let's move on down here. It says smartphones. Big thing here is comprehension. The function p gives the number of people in millions who own a smartphone at t years after the year 2000. All right, so your time 0 doesn't start at 0; it starts at the year 2000. But we're going to graph it as if it starts at 0. So like here it says that p at 2000 or p at 17. Well, that's actually the year 2017, but they're going to say 17 years into it. And they're saying that 17 years in other words, 2017, we have 2,320 million cell phones. So that's what they're trying to do here. At 17 years after the year 2017, there are 2,320 million phones. And at p negative 10, well, that's 10 years before then. Well, when's that going to be? Well, 10 years prior to 2000, which is 1990. There's no cell phones, no smartphones. Didn't invent them yet. Didn't exist. Moving on to number 2, page 148. Just use the function notation to represent the statement. In 2010, a number of people who own the smartphones are, looks like 296,600,000. All right, and so we could put these, if we want to put these in millions. All right, how do you want to do that? Well, if at 10, if you want to do millions, it's going to be a little decimal point. I didn't get much of a decimal point there. We can put it in millions that way, or we could just have it so that it's 296,600. All right, and the input's going to be 10 because we're going to say everything starts at 2000. 2015, our start point is now 15 years, and 1.8 billion, which is 1,860 million. All right, and so that's kind of what's going on here. You go from 296 to 1,890 million in the span of another 5 years. Mai is curious about the value of t, such that the number of cell phones at time t is 1,000, which is the same thing as, you have to realize that 1,000 million is a billion. So what's the value of t to tell Mai about the situation? It's the time t when there are 1 billion phones. Is 4 a possible value of t here? Yes, 2004, and that's assuming that, of course, cell phones were widely available in 2004. And we got a little graph down here. Use information you have so far to sketch the graph. So we have a bunch of points that we have. We had f at -10, there was 0. We said 2000, there was 0. And at 2004, we're like right here. And we had one at 10, we had a number. At 15, we had a number. At 17, we had a number. So it just kind of goes off and takes off like that. Okay. What can one say about the value or values of t when p at t is 1,000? Well, where's 1,000 at? 1,000 is like right there, 1,000 million. Okay, which goes across. It's about right here, so it's about year 12. So that's essentially what's going on here. They're saying that this p, that should be p at 12 equals 1,000. That's essentially what they're going on there. What can you say about the value? And the next page, number 4, boiling water. Alright. So the function W gives you the temperature in degrees Fahrenheit of a pot of water on a stove. And it's t minutes after the stove is turned on. So you take turns with your partner to explain the meaning of each. And so we go through this, and W at time 0, which means the very start, alright, the temperature of the water is 72 degrees. So that's what we got here. What does this mean? Well, it means the temperature of the water at 5 minutes has to be greater than the temperature of the water at 2 minutes. It's pretty straightforward. Here, the water at 10 minutes is equal to 212, which makes sense because water boils at 212 degrees Fahrenheit. So that means basically at 10 minutes it's boiling, or you could say the water temperature at 10 minutes is 212 degrees. And the water temperature at 12 minutes is the same as the water temperature at 10 minutes because it sounds like it's still boiling. Alright, so those two temperatures are the same. The water temperature at 15 minutes is greater than the temperature at 30 minutes, and that's why I've written down here. And the temperature at 0 is less than the temperature at 30 minutes, so it hasn't quite gone down to room temperature less, so the temperature at 30 minutes is greater than the initial temperature. And so we have a little graph here. If all the statements in our previous question are represented in the situation, sketch a possible graph for the temperature. I'll be prepared to show each. Okay. Well, I listed A, B, C, D, E, F over here, and I just have A, B, C, D, E, F over here. So there's A. B is somewhere along in here. There is C. There's D. E is on the way down here, and then F is this little space right here. It's more than what the original temperature is. So something akin to this. And that's the summary of this. It's pretty straightforward. What does the statement like P at 3 equal 12 means? It means that your input is 3 and the output's 12. We don't know what P is. It could be pressure, it could be temperature, it could be height, it could be about cost, it could be about anything. But until he tells us what the function P is, we don't know. We know the input's 3, we know the output's 12. On its own, P at 3 equals 12 tells us that P takes 3 as an input and 12 as an output. Yep. And we know the quantities of input and output. However, we can learn much more about the situation as the function presents itself. And then it goes through. It's got a lot of review here. It tells you about the function. Big thing here. P at 3 at 12 means a square of those sides at 3 inches is a perimeter of 12. So they're saying that P gives you a perimeter, which is the distance around something. Of a square, the side's length, x, and both measurements are in inches. So remember, it's a square. So every one of the sides is the same length. So if it's 3 and 3 and 3 and 3, you can add those together and you'll get 12. All right? We can also interpret them like this. If the perimeter around this is 32, what's the sides? Well, let's see. If I've got side S, side S, side S, and side S, that means the perimeter, which is based upon the side S, is 32. Well, that also equals 4S, because you have 1, 2, 3, 4 S's, so you know it's 4S. So you divide both sides by 4 and you get 32. Well, here they put in an X instead of an S. But then you get this. Alright. If a function P gives the number of blog subscribers in thousands, X months after a blogger starts publishing it, then the number of subscribers in thousands, the number in thousands means there's 12,000 subscribers, and the 3 represents the 3 months. Right? And it goes through some more examples along in here about doing the summary on it, so I won't bore you with it. You can read it as well as I can. So that's the end of the lesson 3, and so I'll move on next to the practice problems.